Okay, today we are going over a faster matrix multiplication using a GPU. And this is using coalescing memory as well as shared memory. And I'll go through what that stuff means. Today I just decided to copy the code here and I'll go through it line by line. So this is the kernel code, just like the previous one. Kernel code, just like we had this kernel code up here. This is the stuff ran on the GPU. The code ran on the GPU. Everything that's in the host, all the host code, is going to stay exactly the same. There was one fix I noticed after my last video. It is grid dimensions by block dimensions. I had it as block by grid, so I had it backwards. This is the correct way. The only other change you're going to make is using the correct kernel. Yep, that's it. Okay, so going up here, we're going to, these first two you could skip if you want, and just, they only get used right here. And you just do block index.x right here, block index.y right there. But yeah, it just makes it a little cleaner. Use these four to make it, cleaner. So block index.x, which is the, if you think of the grid, let's say this is our output here. Let's delete that. This is our output here. And say that each one of these x's is a 32 by 32 block. And so the whole thing here is a grid. Each x is a block in that grid. This bx would decide which block you're in on the x direction, so this way. The by block index.y is the y coordinate. Put them together, you could find, let's say bx was 1, 0, 1, and by was 2, 0, 1, 2. Put it together and you get this one right here. Okay, so that's in case I didn't go through that before. I don't remember now. You get the row and column, which is going to be every thread put together, or deciding which thread is going to be a combination of row and column. So each thread's going to correspond to a certain output, basically each spot in the destination matrix, which will be obviously, so yeah, it makes sense. Your row is block index times block size plus thread index y. This is just the y component of finding where your thread is at, or equivalently where the spot in the matrix, the output matrix. Column will be using the x values. Next, we've got the sum variable, which this will be you'll have a sum variable for each individual thread. That's important to note. And then here's one of the two very major things. You'll do this shared float of A's and of B's. There'll be mini matrices of block size by block size. And why that's so important is because the most slowing down, okay, that's a bad way to put it. The slowest part of using a GPU to do matrix multiplication is the memory reads and writes. These three matrices live on RAM, which it takes a long time to get the data from RAM down into essentially cache, like L1 cache, which is essentially what these are on, and then into calculating. So RAM takes forever to pull from. So that's why you have these shared float matrices, which are, it's essentially like, it's called shared memory, and it's essentially like L1 cache. If you don't know the different layers of cache, or if you don't know cache versus RAM memory, essentially small bit of memory that is right next to the CPU, or it's in your CPU, whereas your RAM is on your RAM sticks far away. This is on the CPU for L1 caches on CPU for kind of that thing, and shared memory is directly on GPU. This is shared memory, which is on GPU. I was just making a comparison. Hopefully that wasn't confusing. Okay, so shared memory, much faster. It's right on the GPU. So what we're gonna do is, okay, so you have a for loop, and the first thing we're gonna do is copy the portions of the large matrix, or matrices, here the A and here the B, copy that into the little matrices. So copying it from high level RAM into the low level cache or shared memory, which when you calculate, taking from shared memory is going to be so much faster. And okay, so when I was thinking about this, I was thinking about it the wrong way at first. I was thinking, okay, you're at thread 0, 0, which would be here also 0, 0, and going through the for loop. And that is not the way you should think about it. You should think about it as, okay, you're at thread 0, 0, or no, you think about it as, okay, so this is a matrix 32 by 32, and when you're in this first loop of the for loop, first time passing through this for loop, you're going to calculate each and every one of the spots of this matrix, or you're going to fill up this matrix one time with the values from the A matrix we have here, for example. You can do the same with the B matrix as well. But so what you do is, this is going to take a little, basically a block. Basically what you're going to do is you're going to set this little matrix, which is going to be a 32 by 32, and it's going to be the same size as this block, because remember my illustration down here, we had 1x is a block and the whole thing together is a grid, which makes up all the threads that would or equivalently, that makes up the entire matrix. So this whole thing is going to be equal in size to this one block, which you can think of this as one block. You'll take one block, throw it into this little matrix, and same here. And then once all the threads have thrown all that into this shared memory for each one, also have boundary checking so that everything outside of the proper matrix is set to 0, so it does not contribute. Then you sync the threads. Basically, this says if one thread is done and another is not, you're going to wait for that second thread to finish. Otherwise, crazy stuff could happen if the first thread starts trying to do stuff. And then here, remember, you've got a sum variable for every thread, which means one way to think about it is right now, when you're doing these guys, you could picture this as just sum plus equals one spot of A's times one spot of B's. Sum will be the same dimensions as these guys, because remember, this is the size of a block. So, and this sum is initialized in every single thread. So it's also, you could also put them together in blocks, because every thread is put together in a block. So this would be a 32 by 32, adding in, it starts from 0, the first one, adds in a 32 by 32 times 32 by 32, element-wise, not matrix multiple. And then once you do that, you sync the threads, and then you're going to go to the next block. So you do the first one, you go to the second block. So for A, or we'll do this in the destination. You do the first block, and then go to the second block. Excuse me. You do the first block, which isn't the first time going through the for loop, and then the second block, and then the third, because M goes from 0th block to, if this looks familiar, that is the, it's kind of like how we did, yeah, it's exactly like how we did this right here. It's the same as the grid dimension. So yeah, you go through the blocks. Yes. Yeah, so one time through the for loop, calculates a whole block, and then the second time, you replace these A's, you replace the B's with a new thing of memory, and then you go through and calculate second block. After you've added in each time, so this sum is a you can think of it as remember, I think of it as a block of sums actually, because there's one in each thread. You have gone through all the blocks and added up the threads, or added up from these matrices in a matrix multiplication, and then you set each of the sums to its destination spot. And that's all there is to doing that. I mentioned the Elliot Arledge video. He has, in part of his video, he does this exact thing, except I think he might just do A's as a block, one block rather than a block by block. So 1D array, I don't remember, but then he would have adjusted the code in here for that. But yeah, that is all there is to that.